Welcome back to this series, everybody. Today I want to do two things. The first, which is you are already seeing on the screen, I wanted to show you the first test of control flow. I will be running a very simple program that has an unconditional jump and updates, increments some registers, just for us to see the blinking lights. I'm not going to test the conditional branches yet. I want to reserve that for a future episode. And I also found during testing two problems that have already been corrected in the repository. They require no change to the PCBs. They only required swapping out one chip for another that fits in the same socket with the same wiring, and reprogramming the flashes because I made a small mistake in the instruction set definition. It would still work, but not as well. So let me show you first the test of the control flow. So I want to show you just one example of control flow. I'm going to show you a unconditional jump being executed in Talos. I will leave the conditional branches for another video because I want to show them together with showing real programs running, with if-then-else equivalent statements in assembly code. But I just want to show you the unconditional jump because it's a nice illustration of the blinking lights. And then it also proves that the jump address register and the program counter, that they can be controlled correctly by an unconditional jump instruction. So this is the little code I typed in. In address 0, we have opcode 7, and opcode 7, you can see here, it's AR1++. It basically increments the contents of address register 1. So once it's incremented, this will count. And then in address 1 of the instruction memory, we have opcode 8. And opcode 8 is AR2++. So it increments the other address register, which is in here. And then in address 2 of the instruction memory, we have opcode F1. And then if you go to the instruction set spreadsheet, here, hexadecimal F1 is an unconditional jump. And what this instruction does, it will take the contents of the jump address register, which is this 16-bit register here. It's actually physically not here. These are just the LEDs, but that's where we will see the contents. And they will be 0. And it will load the contents of the jump address register, in this case 0, into the program counter, which is visible here. So that's an unconditional jump. I already took the system out of reset, and let me take another indicator. That means that we are already seeing the contents of address 0 in the instruction memory, which is opcode 7, the AR1++. So now every 2 times I press the enter, we will have a clock tick. The clock is high right now, as you can see here, the last LED. So if I press enter, it goes low, and it goes high, and then the next time it goes low, we will have opcode 7 loaded into the instruction register. There it goes. And then if I press twice more, now the instruction is decoded. And this is the count enable for AR1. So when I hit enter once more, AR1 will count. There we go. And after that, when the clock goes low, right now it's high. When it goes low, we will have the next opcode coming into the decoded instruction stage. There we go. That's another count enable. That's the count enable for AR2 right now. So when I press enter, AR2 counts. And now, when I press enter and the clock goes from high to low, now here we have the load enable for the program counter. So when I press the clock again, the program counter is now pointing at 3, the third instruction, which is the jump. The jump address register is 0, so 0 will be loaded in the program counter. So let's press it again. There we go. The program counter is now 0. Now, because the program counter is 0, we will have opcode 7, which is in address 0, of the instruction memory coming out of the instruction memory again. But we have two no-ops already in the pipeline. This is a three-stage pipeline. So before we can actually execute the instruction in address 0, the two no-ops have to be, quote, executed. They are no operations, but they need to vacate the pipeline, and this opcode here has to flow down the pipeline. So I have to press enter 4 times before this counts once again. So let me do that. 1, 2, 3, 4. Now it counted. Now if I press twice, this one will count because it's already in the pipeline. 1, 2, and it counts. Now 1, 2 again, and this 0 will be loaded in the program counter because that's the unconditional jump. 1, 2, and there we go. Now the pipeline has two no-ops, so I have to press enter 4 times until this counts again. 1, 2, 3, 4. There we go. 2 more times. 1, 2, 1, 2, and then again 1, 2, 3, 4, and so on and so forth. Now if I keep pressing enter and let the system run, that's what we get. And it's a nice illustration of the whole control flow. Now, we can take advantage of the fact that we know that there is a delay for the jump to actually bring the instruction in the jump address into the pipeline, into the execution stage. It has to pass through the decode, through the fetch and decode stages first. So we get 2 cycles. Now, what you saw us do was to just execute a no-op in there. But instead of that, we could do something smarter. So let's put on address 0 of the instruction memory the opcode 7, which is AR1++. And before, we poked opcode 8 in address 1, which is AR2++, and then we jumped. What we are going to do now, we are going to poke F1, which is the actual jump, in address 2. And then we will put in address 1, and then we will put in address 2 the AR2++, which is opcode 8. And what will happen is that the AR2++ will already be in the pipeline before the jump can bring the opcode from address 0 back. In other words, this will always be executed because it's in one of those 2 vacant cycles that we have before the jump actually executes. This will be already in the pipeline, ready for execution before the control flow goes back to address 0. That's the idea, and this is much more efficient because instead of executing no ops, we actually execute something useful in that time that we have anyway. So let me take the system out of reset. So now here we go. Opcode 7 is coming in. It's in the instruction register, now it's being decoded, and now we have the decoded value. So in the next cycle, AR1 will count. There we go. It has counted. The program counter is pointing to address 2, but we already have the operation in address 1, which is the jump. It's already in the pipeline. It's already in the instruction register. So that will now execute. So that's the load enable for the program counter that will load 0, because 0 is what is in the jump address register. Once that is executed, the program counter goes back to 0, but remember it was pointing to 2 just before, and that 2 is now in the pipeline. So what you will see is that AR2 will count before we count AR1. There we go. AR2 has counted. And now if I let it run, you will see that it will run faster. If I press enter and keep pressing it, it will run slightly faster. I mean, the speed is still determined, of course, by the speed of the key repeat. I'm just pressing enter continuously. That's the bottleneck. But instead of having one no-op, now always executing on every cycle of the loop, Now we have a address register increment in there, doing something useful. That's how you program pipeline machines in assembly. You take into account the cycles you have for an instruction to finish executing, and you fill the pipeline with something useful before that. Of course, you have to pay attention to possible hazards. Like if you have a conditional jump, you have to pay attention on what you execute before you take the jump, because if that instruction that you want to execute is conditional on whether you take the jump or not, like in a conditional branch, it will be executed regardless. So it's nice to fill the delay slots in the pipeline with things that have to be executed unconditionally. And in this case, the address register increments are unconditional. I wanted them to be executed anyway, so I just put them in the little delay slots. So the first problem is just that I used a wrong chip over here. This is the simulation test bed for the control card. Here you have the decoding memories, the decoded instruction registers or DIRs. Then you have buffers here, and then here you have the control signals that go to the other cards and control the other cards. The problem is here in this chip. So if I zoom in a little bit more, here's what happened. I'm using a 7432. I'll zoom in a little bit more yet. This chip here, and if we open it up, you see that these are OR gates. And indeed, the logic I need here is OR logic, because what I want to say is the following. Here's the 7474, which is flip-flops. And if we open it up, this is the clear signal. These two are clear signals, I believe. Let me check. Yeah, clear 2, and this should be clear 1. Yeah. So what I want is the following. I want this flip-flop here to be cleared whenever clear outgoing mail flag is active or reset is active. The same thing here. I want this other flip-flop, which is flip-flop 1, I want it to be cleared whenever reset is active, or this line here, which is the inversion of the clear incoming mail flag. The problem is that all these signals are active low, including the clear signals here. So for them to be active, they need to be 0. For conf or clear outgoing mail flag to be active, it needs to be 0. And reset is also active low. It needs to be 0 to be active. So to perform a logical OR across active low signals, I need an AND, not an OR gate. So I was thinking correctly at the logic level, but not at the physical level. What I want here is for the output of this OR to be a 0 whenever one of these two signals is a 0. In other words, if either one of them is a 0 or both, the output should be a 0. So this should be a AND gate, not an OR, because an OR is such that the output will be 1 if at least one of those are 1. That's not what I need. So that's the error. It's not an error in the PCB itself. All the lines are correct. They go to the right pins. Everything. I don't need to change anything. Don't need to budge anything. All I need to do is to get rid of the 7432 and then take, let me see if I have it here. Take a 7408, which is an AND chip, and put it there. Here. I pasted it twice. 3 times even. What have I done? These one. No. Wait. Sorry. Copy and then paste it once. There we go. That's what we need. And then just put it in there. Yeah. And then let's open it up to make sure that everything is correct. Yeah, 2 inputs to an AND, the output goes to the clear. 2 inputs to an AND, the output goes to the clear. Yeah, this is it. This is it. So I can close everything again. And this is And this is the circuit that we need. Of course, in the board, I just took out the 7432 from the socket and I put the 7408 there, and everything worked just as it should, as simple as that. This file now, the simulation file, is updated in the repository, and so is the PCB file, or the PCB files, including the Gerber, because although all the lines are routed correctly and the footprint is the correct one, the silk screen is not correct. And the label of the chip in the schematics is not correct. So I changed all that, rebuilt the files and updated them on GitHub. So now this is the so far correct control card circuit. I didn't test the control flow yet, like the conditional jumps, but I wanted to make this update as soon as possible. And the second problem is the following. Here is the spreadsheet we've been using. Recently, I just added this column here, which has the opcode in hexadecimal next to the decimal. Hexadecimal is just a lot handier to use when you're actually using the machine. So these are all the instructions. And as we've discussed before, Talos has ILP, or instruction level parallelism, and it can execute more than one operations in the same cycle, in the same instruction. For instance, these instructions here from opcode X15 to X20, each instruction has two operands that are executed in parallel. Here is a memory read. The contents of data memory pointed to by the address in address register 1 are loaded in register A high, and at the same time, address register 2 is incremented. I've discussed in previous episodes that the correct policy for determining which operations can go together in a single instruction to be executed in parallel is that you should never have in the same instruction a operand, be it a register or a memory location, that is both a source and a destination for different operations in the same instruction, because otherwise you have a race condition. And that's why, for instance, here, AR1 is a source. I'm taking the value of AR1 to address data memory. And AR2 is a destination, because I'm incrementing the value of AR2. So this is correct. What would be incorrect is to increment AR1 while using AR1 to address data memory, because then which value will be used? The one that you incremented, the one that was there before, or something in between? And I can tell you the answer. The answer will most likely be something in between. That will be completely wrong. So I thought I had observed that policy consequently in defining the instruction set. But as I was running the code, testing everything, I realized that I missed several instances of this because I was not paying attention again. Oh man, if my old PhD supervisor is watching this, if you're watching this, Professor, yes, sorry, I think I'm getting old. We all do. I'll try to do better. In any case, I'm very thankful for your education all those years ago and still using it today. So you can see here, I made some annotations here. Every time you see this annotation, we'll write to memory the updated value of, in this case, a result low, the result low register. Because I'm running the test by clocking the thing manually, the system will have time to, in this case, update the value of register low here. Result low receives the result of a subtraction. It will have time to update the value of result low according to this operation, and then afterwards use the resulting value of register low to store it in memory. But when you are running at speed, this register low value here will not have time to stabilize before that intermediate result will be stored in memory, in the address in data memory pointed to by the contents of address register 1. So this annotation here, yeah, this is true when you're running it at very low clock speed. But in general, what this means is that this instruction here with 3 parallel operations, it will not work. You will have an unpredictable result because this is a race condition. RL is used here as a source operand, and it's used here as a result operand. this is not good. Can we make this work? Yes, we can make this work. But the price will be that we'll make the clock speed be half of what it could otherwise be, because the first half has to be the time to allow RL to stabilize, the result to stabilize, while you are storing in memory. And then you have to wait for the access time of the memory, the write time of the memory, until you write the stable result into memory. That's not the way to go. We don't want to penalize everything by halving the clock speed just because we want to execute these two operations in parallel. We don't need to do that. So what I'm going to do, I'm going to remove all these operations that have this error, and there's about a dozen of them. There's another one here that doesn't entail a memory operation, but you can see the same problem again. Look, result low receives the result of a subtraction. At the same time, that will load the contents of result low into the jump address low. So in here, result low is a source operand, and here it's a destination operand. There you go, it's a race condition. Not quite. In this case, not quite. And the reason is because of the way the registers are clocked. This register-to-register operation will always use the previous stable value of result low, and then afterwards result low will be updated with the result of the operation. In this case, it's all right because these are do not entail any memory access operation in here. So this I can actually keep, and I will keep this observation that we have to keep in mind that the contents of RL that will be loaded into the jump address register are the non-updated. In this case, it's not RH, it's RL. Let me correct this while I'm here with you. Yeah, but the memory access operations, they are all a problem. So another 4 here that are problematic, and I have to remove them. This one here, it's okay. It's a register-to-register operation. So in fact, 8 operations. Let's see, 1, 2, 3, 4. This is okay. 1, 2, 3, 4. And I think that's it. Yeah, I will delete these 8 operations, and I will come up with other useful operations to put in their place. That's what I'm going to do now. Okay, it's a couple of hours later. I actually moved to the next day, 4 a.m. I'm up until 4 a.m. I removed those 8 operations that were sort of illegal, at least inconvenient. And I decided not to add new ones. What I did, I left space open for 8 user-defined instructions. So anyone can come into this spreadsheet. I will show you the other sheets in the spreadsheet. There is more to it than you are seeing now. It's all in the repository. It's all updated on GitHub, so you can follow along from there if you want. Anyone can just define 8 new instructions here with whatever instruction level parallelism they want to see, combining whatever primitive operations are not present in the combinations above. And they can do that without taking Talos away from the default instruction set. If I would use the entire instruction set space, all 256 entries, then for anyone to create a custom operation, they would need to remove some of the default instructions. And that's not a nice idea. So now everybody has 8 slots here to define whatever combinations of operations, in other words, instructions they want, without deviating from the standard Talos instruction set, without breaking compatibility with other Taloses that will be around the world. That's the idea, and I grouped them at the end for convenience. Of course, this spreadsheet here, it's meant to give you an overview of the instructions available, including all the control bits that are set to 1 or 0. And this works for all the, this is sufficient for all the non-control flow operations, like ALU and register-to-register operations, even for a non-conditional jump like this. you have enough information here because the jump will always set the program counter load enable unconditionally. But for the conditional jumps, there is a lot more going on and that you cannot see on this sheet right now, because although I put the program counter load enable active, this is actually a cheat, because the program counter load enable will only be active for certain combinations of flags. Remember, there are 6 ALU flags and 2 mail flags, the incoming mail flag and the outgoing mail flag. And those 8 signals, they are part of the address of the decoding memories. So we have to set the program counter load enable here depending on the address. And each of these rows here in this table actually expands to 256 other rows. Because for this given opcode here, say this byte in binary, for this opcode, there will be another byte, the least significant byte in the address. This is a 16-bit address, and that least significant byte will be made up with the ALU flags and the mail flags, 6 plus 2, 8. And that's what you see here on this other sheet of the spreadsheet. This is all in the repository. You can see it out there. And what you see here is exactly what I told you. So for each opcode, say this is the opcode 0, there will be 256 rows for the opcode 0, which is an OOP, because we have to take into account the flags, which are in this yellow area here, the outgoing mail flag, the incoming mail flag, the carry flag for the high byte, carry flag for the low byte, sign flag high, sign flag low, 0 flag high, and 0 flag low. Now, for the non-control flow operations or instructions, this is all wasted memory space. Why am I doing this? Well, because you cannot buy small memory chips anymore today. The minimum you can find is 32K, but you can buy 128K flash for less than €3. Those are the flashes, the flash chips I bought, and they are 128K. And here I will be using only 64, so even half of those. So there is no point in adding logic to save on this waste here, because this waste, we are forced to waste memory anyway, since the minimum sizes of the memory chips we can buy for flash, the minimum size is just about 128K now. For SRAM, you can still find 32K. So this is rational waste, because you will waste it anyway. So you better waste it in a way that saves logic. If you're doing an implementation of Talos in an FPGA and you want to use the embedded memory inside the FPGA array, that's a different story. Now you don't want to waste that anymore. Now you want to separate data flow from control flow and not multiply each row 256 times for the data flow operations. And you do that only for the, I think, 10 or 12 control flow operations, and that will save a lot of the embedded memory in the FPGA. But this becomes significant when you go all the way down. There are over 65,000 rows in this table. So those are the user instructions. These are the jump on flags. So for instance, when you have these conditional jumps here, in this case, it's jump on not 0 for the low byte. So here you want to set the PC load enable. Let me see if I can find it here. This is the row. And you see then now that you have ones and zeros, because in this case you want to jump. In other words, you want to enable the program counter load only when this is a jump on not 0 low, when the 0 flag low is 0. And this is the 0 flag low here. So only when it's 0, like in this row here, then you jump, meaning you set the program counter load enable to 1. And for other conditional branches, like this is jump on carry low. So the program counter load enable should be the case only when the carry flag low, here's the carry flag low. So when the carry flag low is 1, such as here, then the program counter load enable is 1, otherwise it's 0. So that's how we set the conditions, by determining the control signals based on the full 16-bit address of the decoding memories, not only on the opcode, but then on the values of the flags as well, which is what you have in this light yellow area here. This is how this stuff works. And once we've done all this, then this is just some Excel operations. You just concatenate the bytes for the opcode. Let me see here. Yeah, you just concatenate the bits for the decoded instruction word, which have 4 bytes. So this is 3, 2, 1, and 0. So in this case, I'm doing the decoding memory 3, so that's the first byte. I concatenate those values. If we go there, these are the values that are being concatenated. So you get a binary here, and then this is just a binary to X conversion. Sorry, it's a huge spreadsheet. So this is a bin to X. That's what you see here, binary to hexadecimal, to do a conversion. Here it's only 0, but here, for instance, you get an actual value. And the order of the bits for Logisim is the opposite of the order of the bits for the actual hardware to program the memories. So that's why I have 2 times 4 rows. Each row is for one of the decoding memories, and each of these 2 sets, one is for Logisim and the other one is for the actual hardware. And then what we use to actually program the hardware is this column here with the hexadecimal values in question. Now you're seeing only 0, but I promise you this spreadsheet has 65,000 rows. Oh, we got to the end. I promise you up there somewhere, let me go somewhere in the middle to show you. So you see here the values get a little bit more interesting, 88 and 10, and that reflects basically what bits you have in each row for the decoded instruction word. That's basically it. These are the changes. Everything is loaded in the repository. So you can already go and have a look at what's changed, but the PCBs, they are all the same. Nothing changed on the PCBs in this latest iteration. So this is it for this episode. I really wanted to put out this episode early this week with the repository updated. Almost everything is tested now. Only the conditional branches are still untested. That's the final uncertainty. But for the coming few weeks, at least 3, I'll be busy with my day job. I have to go on a business trip, and there are some new Argon things that I need to do. It's not the Argon 65X, at least not yet. It's something else that I can't talk about yet, but it's very exciting. So even on the hobby front, I will be busy with other more urgent things and also with my day job. So it will be a couple of weeks before I can release a new Talos episode, but we are on the final straight. We are almost there. Anyway, thanks for watching, and take care.